So I want to mention a specific type of sequence, which is called a geometric sequence. This is something that comes up fairly frequently. A geometric sequence is a sequence whose general term is CR to the n, where C is a constant and R is another constant called the common ratio. So here's an example of what I mean by that. It's easier to see by example. Let's write the first five terms starting with n equals 0 of the geometric sequence where C is 5 and R is 1 half. So recall that the general term is CR to the n. So the first term is going to be 5 times 1 half to the 0. Remember, we're starting with n equals 0, and that's fairly common with geometric sequences. So the next term is going to be 5 times 1 half to the 1, and then the third term will be 5 times 1 half to the 2. The fourth term is 5 times 1 half to the 3, and the fifth term is 5 times 1 half to the 4. And the way we would label these is we would say that this is n equals 0, n equals 1, n equals 2, n equals 3, and n equals 4. So don't get too hung up on the fact that the ordinals don't match. I describe this as the first term, even though it's n equals 0. I describe this as the fifth term, even though it's n equals 4. It's probably more precise just to identify each term by its index value rather than trying to say this is the first, this is the second, this is the third. So anyway, this of course is going to be 5 times 1, which is 5. And this is going to be 5 times 1 half, which is 5 halves. This is 5 times 1 half squared, which will be 5 fourths. And then here we have 5 eighths, and here we have 5 sixteenths. You can see why 1 half is called the common ratio, because what we have here is if the common ratio is 1 half, each term is 1 half the previous term. 5 halves is half of 5, 5 fourths is half of 5, 5 halves, 5 eighths is half of 5 fourths, etc. Okay, so now let's look at a couple more of these. If we have c equals 1 and r equals negative 1/3, then the first five terms will look like, starting with n equals 0, will look like negative 1/3 to the 0, negative 1/3 to the 1, negative 1/3 squared, negative 1/3 to the third, and negative 1/3 to the fourth. That is negative 1/3 to the 0, because anything to the 0 is 1, so that's going to be 1, negative 1/3. We have negative 1/3 squared, which is positive 1/9. Negative 1/3 cubed is negative 1 over 27, and negative 1/3 to the fourth is positive 1 over 81. So that's what the first couple of terms of our sequence looks like. We put a dot 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 to indicate that it goes on. And as you can see, this sequence, because it has a negative common ratio, it's going to alternate positive and negative. If you imagine instead that we make the common ratio negative 1, I just want to show you what you get then. We've talked about this a little bit before, but let's say that c equals 1 and r equals negative 1. I put c equals 1 in both of these examples just so we don't have to multiply the common ratio by anything. I could have put here that it's 1 times that, but it's not necessary to do so, so I'm just going to omit the c entirely. So this is going to be negative 1 to the 0, negative 1 to the 1, negative 1 squared, negative 1 cubed, and negative 1 to the fourth. And as we've talked about, what this does is it just alternates back and forth between negative 1 and positive 1. So that's going to be 1, negative 1, 1, negative 1, and 1. And you can see, by the way, that this series very clearly does not approach any limit. It just bounces back and forth between 1 and negative 1. It doesn't seem to converge to any one particular value. And in fact, with a common ratio of negative 1, you don't have a limit. I wanted to give you the rule for that, which is for a geometric sequence CR to the n, whether it converges or not is entirely dependent on the common ratio, r. It has nothing to do with c. So for common ratio of r, as long as it's greater than negative 1 or less than or equal to 1, the series converges. Otherwise, if it's less than or equal to negative 1 or greater than 1, then the series diverges. And by the way, we're using these terms that you saw earlier in the case of improper integrals, that we use converge to refer to limits that exist, and we use diverge to refer to limits that don't exist. That's true really for any sequence. I'm just introducing the term right here with geometric sequences. So this is the rule for when a geometric sequence converges. So for example, if I tell you that c equals 100 and r is equal to 1.01, you know immediately that the sequence, if this is a geometric sequence, we know immediately that the sequence diverges because r is outside of this interval.